Good afternoon, everyone. I guess I'm between all of you on lunch. Uh, um, uh, I, I was just thinking like this is a topic that's actually very, very close to my heart. I'm a platforms person for pretty much all my career, and I want to use this time to argue and make a case that if you have the right platform and platform abstractions, then every engineer can be part of this great AI rebuild. And you could all like double up as data engineer and ML engineer instantly, and then the barrier becomes very, very low. And that's the case I want to argue. So if you sort of, I was just remembering if I walk through InMobi's sort of floor, when about 5, 6 years ago, you'd find that the ML function and the product engineering function were actually in two different sections, and they were siloed. They were like doing their own stuff themselves. The touch points were there, but they were independent for all practical purposes. You walk through the floor today, you will see that in a common area, the data scientists and the engineers are together and unlocking the product capabilities through ML every single day in every single sort of sprint and product release. The ML function is enabling and unlocking the product capabilities through this integrated sort of approach. Now, what is leading this transformation, if you ask? There are many factors that might be sort of influencing this. I want to talk a lot about how is platforms enabling this transformation? How is platforms enabling for this new org structure, the product development structure, to actually be successful? So when we talk about platforms, we're largely looking at 4 fundamental pillars that we want to focus on. One is platforms typically tend to have good abstractions to hide away complexity. That's what allows the entry barrier to be low and people to be able to sort of do something easily. The second is a lot to do with for an engineer, about if I were to just look at the 80-20 principle, if I take 20% of my time to develop something, 80% of the time actually operationally managing it, right? So you want to make sure that it is up, it's healthy, and it's doing what it's supposed to be doing. So the operational aspect is a significant cost that you pay. So platforms can enable this operational management to be simplified. The third pillar is inherently they enable you to sort of avoid redundancies, cut costs, and make sure systems are efficient. And finally, because there is a common way of doing things, and it enables you to perform your engineering function in a certain way, it's able to bring the best practices in, allow you to adopt them more easily with a low barrier. So those are the 4 pillars. Now, if you were to look at each of these 4 pillars and talk about why they are important, what problems do they solve? So complexities is the entry barrier for people to sort of take up new things, or enabling that journey of every engineer doubling up as a data or an ML engineer, right? So complexities can take in the form of operating with large scale, or complexities could be in the form of managing infrastructure. You have compute on the cloud. Let's say if you're using, there are different kinds of SKUs, different storage, different memories, and from a cloud storage standpoint, you would have things like the lifecycle management of the object stores, throttling, throughput issues, or what have you. So there are a number of problems that you kind of run into when you try to leverage and use them, right? And you also have use a ton of open source frameworks, in your daily work, and they have a lot of boilerplate codes, configurations and defaults. There are like gazillion of them, right? So you're overwhelmed by it, and many times you just copy over code from an existing working stuff and then try to create something new from it. Now, these all add complexity because you're not able to reason or understand with that quickly, and somebody picking up the code is wondering why is it this way, right? So they're not able to understand that. Right? There's a lot of history to it. And hiding all these complexities is very, very important for somebody to be able to get into this role of being a data or an ML engineer. One elegant way to do this is to create abstractions that hide away this complexity. It's about creating opinionated interfaces for people to use that are generally optimal for most of the scenarios. There are scenarios where it may not be working great, but it is generally performant, generally efficient, and works good. And behind the scenes, it can be intelligent about the decisions it is making. And these are a very important characteristic or important pillar that we need to have. So the ability to hide away complexities through abstractions. The next thing I already spoke about, how operational aspect could be significant in terms of the mind share and the time it takes. In a data engineering or a ML engineering pipeline, people have feature engineering, applications, model training applications, inferencing. You also need to look at things like drifts and such. Each of these, if not available out of the box or convenient for you to use, would take away a significant amount of your time in managing this. So you need a way to able to identify root cause and resolve these issues very, very quickly. A good solution for this is much needed. So observability and a good, robust alerting mechanism for you to catch these problems is key, whether it is watching your workflows, watching your pipelines, or your infrastructure metrics. You want to hide away a lot of that, but you still want to have them available in case you want to dig into it. And ability to stitch the layers of the software across through integrated lineage, for example, are all necessary for us to build that muscle around operational robustness. And how do you sort of bring it out of the box for people to then be very efficient with it, right? The third aspect is avoiding redundancies. Of course, we all understand redundancies in code fairly easily. A lot of frameworks that we use in code allows us to be very efficient with how removing these redundancies. But there is a proliferation from a data standpoint. Particularly in the data and ML world, you will find that somebody is working on a model, they need features. They generally end up creating their own sort of data preparation, and create the features without knowing or aware of the fact that somebody else has already got that feature built and it is available for you. Having the ability to discover, having the ability to leverage that existing asset, and then similarly about attribute propagation across the tables while doing the data transformations, for example, is another area. So all of this causes a lot of redundancy, cost and wastage, and more importantly, it can also cause inconsistencies in the outcomes. So that is very, very detrimental, hard to debug and triage. So you need an ability to have a common infrastructure like a feature store to be able to allow seamless discovery and leverage. I also need ability to have data available in a catalog and enable discovery and all that. These are probably things that you would have anyway being used as a data and ML engineer. But if every engineer has to develop as a data and ML engineer, then these are like must to have for them to be efficient and do their function very well. And lastly, deploying service through CI/CD is a very, very well understood facet. And there is, everybody follows a very, very standard mechanism right now. But when it comes to data applications, there is not much standardization, and there is a lot of bespoke solutions being adopted. And there is also things around taking a model out to production. How do you standardize that? How do you standardize the observability around that? Those are all areas where people have adopted custom solutions. Having a common solution for this drives or reduces the barrier for people to sort of double up and be able to be efficient in this role. Now, what I want to do is, having talked about what are the key pillars for a platform to solve for an engineer to be very efficient and what problems it needs to solve, I want to take a look at what the InMobi's data and ML infrastructure looks like behind the scenes. My goal is not to do a deep dive of every stack and every component in there, but to see how all the problems and the solutions that I spoke about a few minutes ago, we're able to tie those ideas back into practice and leave you with the thought of how a platform, if built well, can address these problems elegantly. Of course, it's a journey for us. We're still in the process of sort of building this out, and there is a lot more to be done. But there is a directional sense of how we are addressing these on a continuing basis. So if you look at it, we basically look at three kind of personas. You have scientists, engineers, and analysts. They use the platform to perform all the typical data engineering, training functions, and also inferencing, etc. So there are a whole bunch of things that are happening under the hood. And behind the scenes, there are a lot of open source frameworks, a lot of commercial offerings, and infrastructure capabilities that we kind of leverage. But what the platform as such exposes is these four fundamental things, right? One is it has opinionated APIs that allow you to sort of interact with the rest of the platform, right? These opinionated APIs are, like we said, talked about in the abstractions. It allows you to hide complexities quite a bit, and it is generally performant for all the functions. And more importantly, because you're using this opinionated API, you basically get a lot of stuff free from the platform because it knows what your intention is in terms of how you're using it and leverages that underneath, right? The second aspect is without being, this is super important. Every platform has to be self-service inherently. If a platform is not self-service and it needs to have a lot of touch points with the developers, then it looks more like a solution and it requires constant sort of integration to work with. So fundamentally, it being self-service is a very essential attribute. Third, observability across every aspect at every layer of this stack. The observability has to light up. We already discussed the 2080 mind share, and observability is a key element in addressing that operational robustness or manageability aspect. And lastly, when you talk about opinionated API, you basically are fixing what the platform looks like and what capabilities are available through those opinionated API. Now, if you do not have extensibility, what happens is you basically hinder progress. Every new change, every new thing that needs to be done, somebody has to come back and evolve the platform before they can leverage it. So though you get a whole lot of things free, you basically impede velocity by not having the ability to extend the platform. So you need, on the user space, have the ability to extend it when the need arises so that you don't become the bottleneck. And finally, one thing I do want to make a point is across these layers, you don't have a singular offering that just works, and there are commercial offerings perhaps that you could use that is integrated. But if you're using a myriad of tools to piece them all together, it is important to stitch the context across these layers for it to make sense. Otherwise, it's just a combination of tools. You don't want that. You want it to look like a integrated platform. For that to happen, you need to stitch the context across these layers seamlessly. Right? That's an important aspect. So let's talk about some touch points. So there are two things that I want to talk about. One is the authoring flow, like what does a developer or engineer, how do they interact with the platform? And once they have authored, what happens afterwards, right? What do you get for free, right? I want to break this up into two parts. Like I said, I don't want to go into too much details of what the platform, what we have built inside, but I will get into some aspects of it to just illustrate the idea. So if you look at it, the primary sort of layer that we have at InMobi for data engineering is called the Oxygen. It's basically a wrapper for performing all offline application orchestration in the system. So you basically create a simple view of everybody is looking at data, performing some operation on it, and is executed on a runtime which is backed by some resource. You just create these fundamental simple abstractions without having the users worry about, or without having the engineers worry about where is this runtime, how do you sort of provision this, how do you track it, none of that, right? All that complexity is sort of hidden. And again, from a data standpoint, you don't have them worry about what format, where is it hosted, how do I manage throughput and all that, right? So you don't worry about all that. So you basically convert them into logical sort of constructs and allow engineers to express their intent through this. And this is used for all the offline applications, whether it is feature engineering pipelines, just data transformations, whether it is model training or drift detection pipelines and so on, right? Or model monitoring. All of these are happening as a data application wrapped behind the Oxygen wrappers. The next aspect comes relating to the model training itself, more specifically. So while model training in Oxygen is just an application, if you want to sort of peek into that application and see what is inside that, you basically have a layer, a wrapper called Omega, because that's basically a way to allow you to understand behind the scenes what goes inside training a model, and how do you validate a model, how do you monitor the model, and so on, right? So there are a number of elements within it, and we basically allow our engineers to conveniently build a feature, allow them to register, allow them to materialize in the online serving flow, allow them to build a model architecture that is completely up to the scientists. So that's open completely. It's like an open interface for people to implement. And rest of it, it's sort of is available off the shelf, right? So you don't do a whole lot of stuff write a lot of code. All the boilerplate is sort of removed, but these are all extension points also. So if you want to extend the behavior, you can sort of do that. So what happens is you basically write your application, a training application in Omega, and then you wrap them in Oxygen, and then you deploy it, right? So that's what you do. So once that you have authored this, what happens behind the scenes? Let's talk about that. I'll show a bunch of screenshots and elements of our platform, how it looks like. They're largely to just illustrate the idea and in terms of what happens behind the scene. So this is largely around the operational aspect. So you write the feature engineering pipeline. Mostly in our case, it's almost 100% Spark application. Right? We use Spark everywhere. So the observability around Spark is focused heavily on identifying problems as quickly as possible. Our goal is to not have the engineers spend any time on this dashboard, but to come in, find the information, and go away, right? And the alerting mechanism is largely built with this singular goal, right? So in fact, most of the observability is built with that principle, saying that I don't want you to be in this dashboard for more than few minutes at all, right? I want you to figure out things and then just go away from here. And just because you created the application via Oxygen, suddenly the context from what DAG, what task, what instance of it, all of that starts flowing in, and you're able to sort of look at it from that, and you're able to sort of look at historical trends of that. And you can also look at, if you want to get a little curious, understand the infrastructure utilization of how your application, look at bottlenecks and skews and so on. So you're able to sort of do all that. And the Omega layer is able to look at it from the training aspect. So it's able to say, hey, you were training this model for this set of hyperparameters for this run. This is what is happening. This is how you're using the resources. This is your loss function. This is your accuracy and so on, right? So you get all those metrics directly. And you can, you're in a place where you're able to sort of iterate over it across different parameter tuning, and then you're able to compare them and figure out which model do you want to actually productionize at this point. So you're able to sort of do that. All of these are like seamless handoffs. The developer is integrated, is working with an integrated step at the beginning in the authoring flow. From there on, it's just sort of a completely automated and seamless flow from there on, right? So once you finish this, you figured out the model, you figured out the one you want to productionize. It's available now in the model registry for the inferencing to pull up, but we need to sort of flight that model. We need to create a ramp, rule for it, and flight the model. And once you conveniently flight it, you can watch the model drift and the behavior of that model on a continuous basis through our control plane. So this is another aspect where the handoff takes in, and there is a context flow, right? So you basically have the context from oxygen flowing into Omega, and from the model it is flowing into the experimentation, and from the experimentation it goes into the inferencing layer. So now the model is ramped, and then it goes to the inferencing layer, and you start looking at model performance, the prediction latencies, what the tail latencies are there errors, what's the model refresh rates, and so on. So it's like a continuous flow, and you don't sort of have to do much in terms of all these processes. It's sort of orchestrated and automated to a large extent. These are very important, at least for us. I'll talk about the scale numbers in a bit, but we have trillions of inferences that happen in a single day, and even a 0.1% error rate can have serious negative consequences, right? So just to put that in perspectives. We have some also similarly work being done on feature drift monitoring and have alerting around that. This is still an evolving area for us, very early days in this space, but it just talks about how you sort of build all that. So just also to add what happens from a scale perspective, and what is the scale sort of background with which we are working. We have about 30 billion raw events being ingested every single day, more than 100 models that are at experimental stage at any given time, around 20 trillion inferences being done per day. We have a very stringent latency constraint. Sudhir is going to talk later about a particular problem and the optimizations that are required for that to work at the scale. We also have spent like millions of CPU hours every week in training. Not much on the GPU front for us, largely still on CPU. So before I just want to close and sort of bring this together, right? So we spoke about all this data generation pipeline, the training workflow, the flighting a model, and the inferencing. And you also saw all these components that we used in that. And largely, you see our wrappers in there and some kind of programming interface that the scientists and the engineers are actually using. So you don't hide that you're actually coding up in Spark, or you don't hide the fact that somebody is using PyTorch or TensorFlow. You don't abstract those. Those are the frameworks that people are familiar. You use them. But then what you hide is a whole bunch of tool set behind it, right? So people don't know that there is a whole army of tools, or a whole set of tools that are running behind to enable this platform to do what it's doing, and they don't get to see this. Then that's where the power of hiding all of this comes, and you just enable them through those opinionated API and make all of this kind of possible. So the case I'm hoping I'm making here is that if you were to look at a typical data and ML platform with an open core, and a lot of tools that you kind of use, you will find that it is very complex and difficult to use. But then if you're able to put them all together and connect the dots, stitch them together, and integrate it in the developer flow, acknowledging what they intend to do and how you can enable them to be simple in their operational journey, enable observability, then you can unlock productivity, you can accelerate business outcomes and product delivery, and you can improve operational efficiency and cost efficiency as well. So that's the point I just want to leave everyone with. Thank you.